Now we discuss what is known as boundary conditions. So far we have considered the existence of electric fields in a homogeneous medium. When we say the homogeneous medium is that medium over which the E does not change at any point in the medium. At any point in the medium. So we are saying that we have assumed that to be the case, but now we want to consider a different scenario where a field exists in a region consisting of two media. So we might have one medium here, and we have another medium here. So fields are crossing this boundary. So this is my field E. So this is medium 1 having sigma 1, sigma 2. Oh, what am I calling? mu1. I think we have not met this one. mu1 and mu2, sigma 1, sigma 2, epsilon 1, epsilon 2. So these are medium having different properties. This is the permittivity, this is the conductivity, this is permeability. We have not yet, I'm not sure whether we have met permeability, but this is the characteristic that tells you how easily the material gets magnetized. But this is subject we're going to be discussing in unit electromagnetics 2, the advanced unit from this one. So having said that, we say now that the conditions that the field must satisfy at the interface separating the two medium are called the boundary conditions. So when the field crosses from here, from this medium A to medium B, then it must satisfy some conditions. And therefore, these conditions are very useful because they help in determining the field on one side, such that if you know the field on this side, like E1, you know, but you don't know the field on this other side. If you know the conditions that relate the fields as they cross from medium 1 to medium 2, then it becomes very easier or very easy to determine the field on the other side if we know fields on one side. And obviously, we say that the conditions will be dictated by the type of material that the medium, each of the media is made of. Therefore, we might have a conductor, we might have the electric one, having, as I have described, having ER1 or E1, and the electric 2 having permittivity or relative permittivity ER2, etc. So this is one possibility. We might have another kind of medium where we have one of them is a conductor and the other one is a dielectric, or we might have a conductor and even free space. So we have three types of medium that we are going to be dealing with. That is dielectric to dielectric, dielectric to a conductor, and conductor to free space. Free space is the one that we considered in our previous lectures, or chapter 4 of this text. And we considered it to have EUR to be equals to 1, and we were only dealing with epsilon naught. Now, to determine the conditions, we will use two of Maxwell's equations. The one that deals with the electric field strength over going through a cross line, and this is in the integral form. I remember we said that we have two forms of Maxwell's equations. One is stated in the integral form. These two actually are stated in the integral form, but I have tried to write them in the differential form, where we say that the divergence of E, the curl of E is equals to 0. And the other one is the curl of D. Just a minute, I need to correct this. How would be that? This has to be divergence. We are using the divergence theorem here. So we are saying that the divergence of D is equals to rho V. So this is the other equation that Maxwell derived, and these are the two equations that we are going to be using to define the boundary conditions. And therefore, this is coming directly from the Gauss rule. We have made that before, and therefore that is not new to us. So since we are dealing with D and E from the equation that we have just stated here, we definitely need to find two forms of these equations, of these two vectors. And it's straightforward again. You can break E to have two terms, two orthogonal components. One is the tangential component, such that, look at this. E is directed towards the direction indicated. So it definitely has the normal component, the one that we say En, and you have another component that is orthogonal to it, that is tangential component. And most of the times, we are going to be evaluating these two. In similarly, D is a vector. It might be pointed to our boundary. The boundary is the one I'm drawing a vertical normal to the field. Therefore, if D is pointed in the direction shown, it has two components: the normal component, dn, and the tangential component, d of t. Now we jump to the Directrix boundary conditions. As we have said, we are dealing with three types of boundaries: Directrix to Directrix, conductor to Directrix, and conductor to free space. So if we start with the first one, where we have two Directrix as illustrated on figure 510. Figure 510 is here. This is medium 1, and this is medium 2, and here is our boundary. So we are going to be considering a portion of the boundary described by crossed line path A, B, C, and D, and the height between the two boundaries is considered to be delta H, and the width of the two boundaries is considered to be delta width. So having said that, we say now that once we consider that, we are saying that the two different directrix are characterized by E1 having E0 and ER1, and epsilon 2, epsilon naught, and epsilon R2 are shown in the figure. Therefore, the fields E1 and E2 in the media can be decomposed, as we have said before, the tangential component and the normal component. Now, from equation 552, we stated here is that the cross-line integral of E with respect to the path element dr, or dA rather, is going to allow us to form E times length. So E1t times length. So we are simply saying we take the tangential component, which is we start with this one. Tangential component from A to B is E1t. Then you multiply by the length of that element, which is delta omega, plus a portion of normal electric field component, which is delta H over 2 times E1 normal. So if you actually look at that, is that, but remember that our E normal is pointing from medium 1, medium 2 to medium 1, and therefore when you go in the direction of B to C, this becomes negative. So that is why we have negative E1 normal del of H. So when we now cross to the other side, to this other side, we get the same component, but it is now the component of E2Fn. So we continue like that, and what we observe is that this is equation 556 that we shall obtain. And when we look at it after we have established all the components of each of the components of electric field E along the different paths, we find out that some of them cancel each other, like the first normal cancels with the first normal, and the second normal cancels out with the second normal. Therefore, we are only left with the tangential component as illustrated, because they have different terms. As you can see, this is E2 of t. And therefore, when we say that, we can always say that the magnitude of E of t is equals to the one that you're expressing as E of t. Notice that this is a vector, this is not a vector, it's a scalar. So we are saying that this is the magnitude, and this is the magnitude of the normal component. We are saying that these two terms cancel out, or the components along the or perpendicular to the interface cancel out, and therefore we are only left with this equation. And therefore, as since this term cannot be equal to 0, we are able to cancel, equate E1t to E2 of t to have equation 557. And this is one of the boundary conditions. So we normally state them as that. And there is a significance of this equation. And this equation says the following. Before we state the condition, we say that's the tangential component of E are the same on two sides of the boundary. That is one way in which you can state the first boundary conditions. But the way we normally say is that the tangential components undergo no change at the boundary, and they say to be continuous across the boundary. So the condition that you normally state for electric field is that the tangential components of electric fields between two dielectrics at the boundary are continuous. That is the word. You must always keep that word. So we are done with the first condition about E1 of t is equals to E2 of t. That means they are continuous. Now, talking about, so the first one we dealt with electric field strength. The second one we deal with the electric flux density, D. And we start by knowing that D is expressed by as a function of E, which the two are related by the electric or the permittivity of the medium. Therefore, we can state from this equation that since we know this is the condition that, or the first boundary condition that we have stated, we can equate to the left the d1 of t over epsilon 1. We know that to be the case from this equation, and therefore d2 of t to be over epsilon 2 to be that, and therefore we get equation 558. Just notice that this is not one of the boundary conditions. You only state it is like a derivative of the first boundary condition. This one, it simply states that the tangential components of the electric flux density are discontinuous. We say tangential component of D, or electric flux density, are discontinuous at the boundary. So that is just a derivative of the first law, or the first statement of the condition. So now from what we have observed is that the dt undergoes, what we have seen from that equation is that dt, or the tangential components of the electric flux density, undergoes some change across the interface, and therefore that is why we are saying it is discontinuous. So therefore they are not the same. From boundary 1, this is material 1, this is material 2. The d of t is different from the d1 of t is different from d2 of t. Therefore, that is say they are discontinuous. When they are not the same, we say that they are discontinuous. Therefore, from equation 553, or similarly, we can apply the equation 553 to the pillbox, or the cylindrical Gaussian surface that we have developed in figure 510p. So we want to do what we did, like finding out how much flux changes we are getting as we go through this Gaussian surface. So remember, for the E field, we looked at the line integral, or the equation 553 that was stating the sum of the electric fields across along a cross line integral is equal to 0. But now for the electric flux density, we consider this Gaussian surface that is defined by a cylinder. And what we say we are in regard to this is that, of course, the flux that is getting in here should be equals to the charge enclosed on the volume or the flux that gets in here should be equal to the surface that the flux that goes through the volume. That is okay. We normally say the Gauss law that divergence of D is equals to rho. So that the what is getting in here should be equal to the what that is getting out there, except the one that is lost due to the charge enclosed. And for that reason, and I'm not sure that is the correct statement of that, but for this I know it's accurate, but we normally say that the flux that is going at that point should be equals to the flux that is coming out minus some that is absorbed by the charge enclosed. And you'll see that as we continue. So we are saying that from this pillbox, that Gaussian surface, we are calling it pillbox. It is saying that the contribution due to the side vanishes as, of course, the sides of the cylinder we consider them to be insignificant in terms of the contribution of electric flux density. But what we are concerned with is that the charge enclosed in the Gaussian surface should be equal to the flux that is coming in minus the flux that is coming out. That is the most important thing. And that is what the Gaussian law states. And therefore, from that point, we can say that the change in flux is normally given by the surface charge density times the surface area. Therefore, if you now look at this equation as it is, you can simply cancel out the d of s, and you are left with d1 of n minus d2 of n is equals to the surface charge density, rho s. Therefore, we have equation 559, and this is one of the other statement of boundary conditions. Notice that we have said that rho s is the free charge density placed deliberately at the boundary. It should be borne in mind that equation 559 is based on assumption that D is directed from region 2. So we are saying that region is directed from here towards region 1. And therefore, if there is no free charges that exist at the interface of the two boundaries, then we say that the rho s will be equal to 0. And therefore, the flux that enters should be the same flux that comes out of this boundary. That is a matter of that we stated in the flux in the Gauss law. Therefore, equation 59 becomes equation 560 because we have lost the rho s to because we have said there may be no free charges, and therefore when there have no free charges, there is no surface charge density on the surface of the boundary, and we end up with the equation 560. This is the second statement, or these two are the second or the other boundary conditions that we normally state. So I have just deleted them here, equation 559 and 560. That they state the boundary conditions due to due to the flux density and due to the electric field strength. The first one is that the tangential components of electric field strength along the boundary are continuous, and the electric flux density the normal components of electric flux density across the boundary are continuous. So we normally state the continuous ones, and therefore if you want to state the derivatives of this, we state the discontinuous one, which comes out that says that the normal components of electric fields, which are stated from equation 61, which is here, is that the normal components are discontinuous because they are changing when you move from one side of the directrix to the other one. And again, from equation 57, we said that if we know this to be the case, we can define electric flux density as a fraction of d. Of course, from this that we can definitely say that if this is the t and this becomes the t, you dividing by that, you end up with the e there, and therefore we say that since we have said e1 t is equals to e2 of t, then we can say that d1 of t will be equals to d2 of t over epsilon 2, and therefore we say that the tangential components of electric flux density across the at the boundary are discontinuous. And that is what you're saying here, that D is continuous across the interface. Okay, the normal components are continuous across the interface. And there's another one where we are assessing the tangential components. I think that's the one we were stating at section 57. It says that the tangential components of the electric flux density along the two medium are discontinuous. So we are say looking at equation 561 as a derivative of equation 560 and equation 57 as a derivative of equation 5. Why is that? Yeah, equation 58 as a derivative of equation 557. So having said that, we can come up with another. So we have seen one of the application of the boundary conditions is that if we know one, like for instance, we know the permittivity of this medium 1 and medium 2, and we know the tangential component of the D in one directric, then we can be able to find the unknown, which is might be that one, or the other, or any other. We can apply either of those equations 5, 7, 5, 8, all the way to 6, 1 to find any of the unknown components, be it tangential or directric. So that is one application of boundary conditions. The other application is that we can use the boundary conditions to determine the diffraction of electric fields across the boundary. So we are talking about that if we know the characteristics of the boundary and we know that either of the electric field or flux are directed from one medium to another at an angle, then both of them are the flux and the field are going to experience some diffraction, and therefore from knowing the boundary conditions, we can be able to determine how much diffraction is going to happen. And we can see from, we are going to consider figure 511, in which case we have D1 and E1. So our D1 is pointed this way, just pointed at an angle theta from the normal of the interface, and D2 is also pointed towards this direction, but it is making an angle theta 2 normal to the surface, normal to the interface. Sorry, the angle is theta 2 from the normal of the interface. So we are not counting from where the interface makes this one. So we are not saying this is the theta 2 or this is the theta 2, the theta 1. No, we are not saying that. The theta 2 and theta 1 are measured from the normal. This is the normal to the interface. So that is the first thing. So that is our first consideration. And then from that, we can clearly write some equations that are relating each of these components, and we can express them in the tangential and the normal components. And if you were to find the tangential components of E or E1 of t, we can simply say that this is going to be the sine E1 sine of theta 1 is this the tangential component, which is we are calling that E1 of t. And we can say that it is from equation 557, we say that it is equals to E2 of t, that they are continuous, and therefore if we find E2 of t, we can simply say that this term is simply E2 of t, okay, E2 sine theta 2. So we end up with this equation at that point. And similarly, we can also say that from equation 5 60, we say that d1n is equals to d2n, and therefore we can try to find the normal terms d1n from our expressions of d1, where we can simply say that this is adjacent. Therefore, if it is adjacent, we can simply say that d1 cos theta 1 should be equals to d2 cos theta 2, because they are adjacent to our angle. And therefore, having said that, so having developed these two equations, which are definitely this one and this one, then we can be able to, we are saying that we can be able to divide this equation 562 with 561 at this point. If you just divide this by this term, you are simply going to find this cancels out. This becomes tan of theta 1, and therefore we have tan of theta 1 divided by epsilon 1. You have on the other side tan of theta 2 over epsilon 2. And therefore we have equation 565 that says that tan of theta 1 over tan of theta 2 is equals to, having known that we can express E1 in terms of the permittivity of free space times the relative permittivity of the medium, the same way for the medium 2. Therefore, we can say that we get equation 565, and this is the statement of the law of refraction of the electric field at a boundary free of charge, because we considered a sigma of S, or free charge surface, okay, surface charge density due to free charges at the boundary to be equal to 0, because we never applied them. And thus, in general, an interface between two dielectrics produces a bedding of flux lines. So if flux lines were coming at, if these are my E, they are pointing at that direction towards this boundary, which has permittivity ER1. If provide boundary 2 with ER2, they are going to be refracted. The concept of refraction comes in. Therefore, it applies normal to the way we see light getting refracted.